Hello and welcome to the second video in our lecture on the TLS protocol. In this video, we're going to start by reviewing the Diffie Hellman algorithm, and then we're going to discuss a new variation, a more secure variation of it. So first, we'll do review part 4, which is the Diffie Hellman key exchange algorithm. Now remember that this is an example. In fact, this is the original public key crypto system proposed in the mid-70s. And because it's a public key crypto system, we're going to assume that the two parties, we're going to call them Alice and Bob as usual, they both have a pair of keys. And so this is going to be, for Alice, is going to be a public key and a private key. And similarly for Bob, he will have a public key and a private key. So we're going to assume that somehow these keys have been established. This is pretty easy to do. We can even consider that there are certificates associated with those keys, so the public keys are considered safe. And so the Diffie algorithm also assumes that the two parties have agreed on two values, namely a large prime number q and a primitive root of q alpha. So assume they've already agreed on those two values before we start the Diffie-Hellman algorithm. Okay, now we have the setup. So the way Diffie-Hellman works is we have Alice on one side of the channel, Bob on the other. So of course this could be our client and this could be our server. And the first step is that Alice is going to pick a random number x sub a. Bob is going to do a similar thing, but of course pick a different random number x sub b. And then Alice is going to compute a new number, which is going to be y sub a. And this is obtained by taking alpha to the power of x sub a modulo q. And then similarly, Bob is going to compute y sub b, which is alpha to the power of x sub b modulo q. The next step of the Diffie-Hellman algorithm requires Alice to send her y value to Bob, and then the algorithm requires Bob to send his y value to Alice. And finally, to wrap up the algorithm, the shared key, remember that this is a key distribution algorithm, so at the end the two parties must have a shared key. We're going to call this key k sub ab, since it's known to both and only those two parties. And it's going to be computed by Alice by taking the value that Bob just sent her and raising that to her own number modulo q. And Bob is going to compute the same key using a different formula, which is the value that Alice sent him raised to his own random number modulo q. And we argued and explained why these two computations are going to yield the same value. So at the end of the algorithm, Alice and Bob have a shared key that can be used in a hybrid crypto system to encrypt using symmetric crypto the rest of the messages. So I spent a lot of time reviewing this algorithm. Make sure if you want to discuss it in more detail, you go back to the concrete example that we gave in class. But there was also one very big weakness for this algorithm, and we said at the time that it could actually not be used on its own. Do you remember what that weakness is? And if not, pause the video and try to identify the weakness of this Diffie-Hellman algorithm. Well, the weakness is that the intruder, the attacker Trudy, can do a person in a middle attack. She can actually impersonate Alice to Bob and Bob to Alice, and essentially insert herself into the key exchange algorithm without the two parties knowing about it. So that's clearly a completely insecure algorithm. And we said at the time the reason for that is because the parties are not authenticated to the other party. So, for example, when Alice receives YB, she has no proof that the sender was actually B. And similarly, B has no idea that A is the party that sent um, this value YA. So, the variation or the improvement that we must make to this algorithm is we need to develop an authenticated variant of Diffie-Hellman key exchange algorithm. And this is what I want to discuss to wrap up this video. So remember what we're assuming, that we're building this algorithm into a hybrid crypto system. So we assume, again, that Alice has a private key and that Bob also has a private key that is known to only each one of these two parties. And of course, they have an associated public key. So we're just going to be using these private keys in this algorithm in order to have each party sign their own communication and therefore prove that they are who they say they are. So then the algorithm that we get is a very small variation of the previous algorithm. And I'm going to only highlight the main part. So remember, we have the two parties. We have both parties know Q and alpha. And then Alice has chosen a random number, so has Bob. And so now Alice is going to be, as before, able to compute her own value of y, and B is going to compute his own value of y. And now instead of sending those values, we're going to send them in an authenticated way. And so what that means is that Alice is going to send to Bob not just her y value, but the encrypted version of it. And to authenticate herself, she's going to use a private key. And similarly, Bob, when he's going to send his YB value to Alice, is first going to sign it with his private key. So this is a simple way where Alice and Bob can authenticate each other while doing a Diffie-Hellman key exchange. So at the end of this algorithm, not only the two parties have a shared key, since they can both compute it using the Y value they got from the other party, but they also have authenticated themselves using public key cryptography. So now that we have this new version of the Diffie-Hellman key exchange that include authentication, we're going to talk about a new concept that is also important for TLS, and that concept is called perfect forward secrecy. And that will be the topic for the next video.